Dear students, today we are meeting for the second lecture for the course COC2070 Digital Logic and System Design. Before I actually start my discussion, I would like to you to notice a point. There are a few things that appear, easier than they actually are. For example, when we talk about the open book exam, it appears that the open book exam will be so easy. I'll have the book with me so I can answer the questions very easily. But the truth is just the opposite. The open book exams are supposed to be much more difficult than the closed book exam. Why? Because the questions will be tough, and then you have to study at least as much as you study for the closed book exam before you can effectively take the open book exam. Otherwise, when the question comes and then that is the first time you start looking at the book, you will just keep searching for the answers and you won't be able to get the answer even when the book is in front of you. That was the example. With that example, I want to emphasize that it appears that online teaching is easier than the classroom teaching. I'm not talking about the teacher's perspective, but I'm talking about the student's perspective. They think that, you know, the online teaching could be where I can, have the recorded lecture, I can listen to that lecture at my convenience and so forth. But let me tell you once again that the online lecture is more challenging than the classroom lecture, because in the online lecture you should at least work as hard as you do in the classroom teaching. So with this I would suggest that even when I'm doing the online teaching, please do make notes just as you make notes in the classroom teaching. Even though I'll be making use of PPTs, but there are many things that I'll be saying beyond the PPTs. If I didn't have to say anything beyond the PPTs, there is no point in giving the lecture. I would simply made those PPTs and shared with you. You could have gone through them and you could have grasped. So I would suggest that do make notes even when I'm doing these recorded video lectures, so that you record each and everything that I'm speaking and you are able to, recall it as and when required. So with that little piece of advice, let me start this lecture. uh, we have been talking about the number system in the previous lecture. Now I'll just continue with the same. First thing is that binary digit is called a bit. Keep that in mind forever. Binary digit, we take bi from binary and we take d from digit. So a binary digit has got a specific name which is called a bit. 8 such bits put together, such binary digits or bits put together, is called a byte. For example, this one contains 8 bits, so this will be a byte. So bit and byte, that should be, in your mind for all times to come. Now, in the previous slides, in the previous lecture, we had seen that whenever you have to change a number from decimal to any other base, there is a procedure for that. I've elaborated. But if you have to change from a generic base m to generic base n, then also you will have to first convert the base m number to decimal, and then you have to convert the decimal number into a base n. But there are a few exceptions wherein you can do direct conversions. Not every base m can be directly converted to every base n. You will have to resort in between to a decimal conversion. But there are a few special cases. For example, one such case is direct conversion from octal to binary, that is from base 8 to base 2. Each octal digit will be converted to 3 bits. Again, this bit, binary digits bit. So each octal digit will be converted to 3 bits. For example, if I'm given a number in base 8 as 437, again don't say it 437, it is not a decimal number. It is a base 8 number. So call it 437.06. So this will be directly converted to base 2 by converting this 4 into the corresponding 3 bits. And by now you must be getting conversion that 4 will be 100. 2 to the power 0 plus 2 to the power 0 into 2 to the power 0 plus 0 into 2 to the power 0, which both of them will be 0, and then 1 into 2 to the power 2. So 2 to the power 2 is 4, so that will be 4. So this 4 will be 100. This 3 again will be in 3 bits. 3 of octal will be in 3 bits, that will be 011, and 7 will again be in 3 bits as 111. After that, you will place this decimal point, and then the 0 will be again in 3 bits 000, and 6 will be in 3 bits as 110. So from now on, you must practice of counting in binary. So counting in binary, that should come to you now. Then only you will be able to do this octal digit into the corresponding 3 bits. What about the reverse? Binary to octal. In binary to octal, for the whole part, combine 3 bits into an octal digit, starting from the decimal and moving rightwards. It should be leftwards. Append zeros at the rightmost part if required to complete the count of 3 bits. So it should be leftwards. And for the fraction part, this should be fraction part. Combining 3 bits into an octal digit is starting from the decimal and moving rightwards. It should be rightwards. Append zeros at the leftmost part if required to complete the count of 3 bits. I'm sorry, this should be rightmost part if required to complete. Let me give the example. So there is some problem with this statement, these statements, but let me give you the example. Things will be more clear. Suppose this is the binary number given, the bits given. So I'll start joining them or combining them 3 by 3. So I'll take this 111. I'll move leftwards 111. Then I'll combine these 3 bits again 001. So after having 001, this is 110 is left. So I'll combine this 110. Since this 0 is insignificant because it is at the leftmost portion, so I can append this 0 here to get a complete combination of 3 bits. Similarly, for the fraction part, I'll go rightwards and then I'll make 3 bits of 3, 110. So it will be 110. I'm left with just a single bit. So I must complete it by 3. So I'll append zeros to the right part. So now I can write it. 011 is 3, 100 is 4, 111 is 7, and this 110 is 6, and this 100 after having appended those zeros on the right hand side, this will be 4. So the conversion from binary to octal can be done like this. Let us take more examples. Things will be more clear. Direct conversion from hexadecimal to binary. Each hexadecimal digit will be converted to 4 bits now. Why I'm doing this, I'll come to it a little later in this slide. Let me give you the example first. 8AC6.10F 16 be converted to binary. So this 8 will be converted to 4 bits. So 8 is 1000. A is 1010 because A is 10 in decimal. So it will be 1010 in binary. C will be 1100. 6 will be 0110. Now place a decimal point. After that 1 again in 4 bits 0001. This 0 will again be in 4 bits, even though it is a 0, but use 4 bits, exactly 4 bits. And F is 1111. So this will be the conversion from base 16 to base 2. Direct conversion from binary to hexadecimal. Again, those changes have to be done in the written part. But let me come to the example. When I'll share the slide later, I'll make those changes and then I'll share the slides with you. So take this example. Start from the decimal for the whole part and move leftwards. So make combinations of 4 bits now. So 1110, 4 bits up till now, and then 0111, so 0111. After having this, you are just left with 2 bits, so append zeros on this side. You can do it, append zeros. That will not make any difference to the number. So it will be 0100. Similarly, starting on the decimal point and for the fraction part moving rightwards, again combine in fours. So 1101. So it will be 1101. Now only 1 is here. So append zeros to its right. So 1000. Now you can do the conversions. 0010 is 2, so you will place a 2. 1110 is E, so you will place an E there. And then 0111 is 7, so you will place a 7, a decimal point. And then 1101 is D. 13, 1101 is 13 in decimal, and 13 in hexadecimal is D. And then 100 is 8. So this will be the conversion of this binary number into hexadecimal directly without required to be converted into decimal. Can there be more such direct conversions? Are these two just the special cases, octal to binary and back, or binary to hexadecimal and back? There are more cases also. Yes, there are more cases. We can do it between 2 and 4, 4 and 16, 3 and 9, etc. The formula is this: R1 equals R2 to the power R2 to the power n. For example, if R1 is 8 and R2 is 2, so whenever there are exact powers, we know that 8 is 2 to the power 3 exactly. So we can do it between octal and binary. Similarly, if R1 is 16, then and R2 remains 2, then it is 2 to the power 4 is 16. This n is important because this n is going to get you how many corresponding bits should it be converted to. For example, in the case of 8, it was 2 to the power 3, so 3 bits are required. In case of 16, 4, 2 to the power 4 is 16, so 4 bits will be required. That is why, will be converted to 4 bits. So this n will give you an idea. 2 and 4, if R1 is 4, then it is 2 to the power 2. So 2 bits will be required if we need to convert from base 4 to base 2. And 4 and 16, if it is 16, then 4 square is 16. So again 2 bits will be required if I am doing a conversion from base 16 to base 4. 3 and 9 similarly can be done. If R1 is 9, then 9 is 3 square, so 2 bits will be required. So likewise, you can go on converting directly whenever you have the the exact powers. And what exact power is that? That will give you how many digits it needs the conversion to. So this is the idea of direct conversion. Next, let me move on to some binary arithmetic. First of all, counting in binary, because binary, I said in the previous lecture that binary is the thing that digital computers follow. So we have to get more conversion with binary, even though we have to know other bases for for our having a strong theoretical foundation. But then practically, this binary is what we are going to live with from now on. Counting in binary, that you should do. 0 is 0, 1, 2 will be written as 1 0, 3 1 1, 4 1 0 0, 5 is 1 0 1, 6 7 8 9 10 11. Likewise, you should know how to count in binary, right? Like 1100 would be 12, and then 1101 will be 13, and so on. So try completing this sequence to for your practice sake till 100 or something like that. So counting in binary, you should be very well conversant with. Addition of two binary numbers. Let us come how to see how can two binary numbers be added. We know that 0 plus 0 is 1. 0 plus 1 is 1. In fact, 0 plus 1 will be 1 plus 0 because addition is commutative. A plus b is equal to b plus a. So 0 plus 1 will be 1 plus 0, which will be 1. 1 plus 1 in binary will be 2 in decimal, and 2 cannot be written in binary as such. So I'll have to take this 2. So 1 plus 1 will be 1 0. Similarly, 1 plus 1 plus 1 will be 3. Again, 3 doesn't exist in binary. Remember, with base r, we can go for digits from 0 to r minus 1 only. So with binary, which is base 2, we can have digits up till 2 minus 1, which is 1 only. So 1 plus 1, which is 3. So I'll have to write it in binary as 1 1. With that, now let us come to adding two numbers. Suppose I have to add two numbers, augend and addend. I have to add these two numbers. So how do I do that? 1 plus 0 will be 1 with no carry. We have seen there, 1 plus 0 is 1 with no carry. Similarly, 0 plus 1 will be 1 with no carry. 0 plus 1 will be 1 with no carry. But when I do 1 plus 1, it will be a sum 0 with a carry 1, because 1 plus 1 is 1 0. So you will place a 0 here, but a carry will come here. Next time when you will add, this will be 1 plus 1 with a sum 0 and a carry 1 again. 1 plus 1, in fact 1 plus 0 plus 1 will give you again 1 0. So you'll place a 0 as sum and a carry 1. 1 plus 1 plus 1. Now this will be 11, not 11. Just keep that in mind. This is 1 1, which is 3. 1 plus 1 is 3. So which is 1 1. So you will place a sum as 1 and a carry 1. 1 plus 1 is again a sum 0 and a carry 1. 1 plus 1 is again a 0 and a carry that will be placed here, because there are not any more things to add to. So this is how you can add two binary numbers directly. This is similar to how you add in decimal. The difference is that in decimal, the carry and the digits could be anything between 0 and 9. And for any generic base, the digits and the carry can be anything from 0 to r minus 1. Likewise, for binary, it can be from 0 and to 1 only. So 0 and 1 are just the two possibilities. And that is why, binary numbers are so useful, because you have mainly two possibilities, on and off, true and false, like that. So that is why we'll see later how do we adopt this binary for our real life situations. Now subtraction of two binary numbers. Can we do subtraction? Yes, we can do. Like 1 minus 0 is 1. All right. But can we do 0 minus 1? No, we cannot do. So what I'll do, I'll try to take a borrow. But this is already 0. It cannot give you a borrow. So I'll do a borrow from here. When I take a borrow from here, this becomes 1 0, which is 2. And then I take a borrow to this side. When I take a borrow this side, remember this 2 will be reduced to 1 and this 1 will be reduced to 0. But taking a borrow here, this will become 1 0, which is 2. And 2 minus 1, 2 in decimal, but 1 0 in binary. So 2 minus 1 will be 1. Now here, what was remaining was 1 only, because this gave a borrow. It took a borrow from here, became 2, but then gave a borrow. So it is 1 again back. So 1 minus 1 is 0. Now this was reduced to 0 because it had given a borrow. It had 1, it gave it away as a borrow. So it was 0. 0 minus 1 cannot be done. So we'll again take a borrow from this side. So this will become 2 now in decimal, which is 1 0 in binary. And 2 minus 1 will be 1. This remains 0 because it gave away a borrow. 0 minus 0 can be done, so that will be 0. Now over here again, 0 minus 1 cannot be done, so you took a borrow from this side. When you took a borrow, this became 2 in decimal and 1 0 in binary. 2 minus 1 will be 1. But then this is reduced to 0 because it gave away a borrow. So again you will take a borrow from this side. When you take a borrow, it becomes 1 0. 2 minus 1 is 1. But this is reduced to 0. So you'll again take a borrow from this side. When you take a borrow, this is left to 0, but this becomes 1 0, which is 2. So 2 minus 1 is 1. And this was 0, so 0 minus 0 becomes 0. So this is how I can do subtraction. Just as with other like decimal numbers and other, you can do a cross check by adding these two numbers and seeing if this is coming out to be all right. That is what happens in binary. If a minus b is c, then you can do c plus b to get a back. So just try that, because addition is easier than subtraction. So this was my difference. So let me add it. So 1 plus 0 is 1. All right. 1 plus 1 will be 1 0. So a 0 here and a carry 1. 1 plus 1 will again be 1 0 with a 0 here and a carry 1. So 1 plus 1 plus 1 now. So that will become 1 1. So a sum 1 and a carry 1. Now 1 plus 0 will be 1. No carry. 1 plus 1 will be a 0 with a carry 1. 1 plus 1 plus 1 will be 1 1. So a 1 here and a carry 1. So 1 plus 1 plus 1 will be 1 again. The sum 1 1. So a sum 1 here and a carry 1. And 1 plus 1 plus 1 plus 0 will be 1 again. So this is how subtraction of two binary numbers can be done and then cross check, just as you had been doing a cross check in the case of other bases. So you have to get conversion. I'm just giving examples. You have to take several such examples and practice for yourself to see whether this is coming out to be all right or not, right? So you have to practice a lot in order to get to the actual thing. Binary multiplication. Can we do binary multiplication directly? Yes. This is the multiplicand, this is the multiplier. Just as we do in decimal or other bases, I have placed the multiplicand here, I have placed the multiplier here. The first step, I'll multiply this entire thing with 1, which is easy. This will be simply copied. Anything multiplied with 1 remains the same thing. So 1 1 0 1 0. This thing will be copied here. Next time I am multiplying with 0, and anything multiplied with 0 will be 0 entirely. But I must place a cross here because it should be shifted by one place before I add it up further. So I'll place 5 zeros because it is being multiplied by 5 zeros, and then but I'll place it after one cross. Now this third bit, when I'm multiplying, I'll place 2 crosses here, and then I'll multiply by 1, and multiplying by 1 will be simply copying it. So 0 1 0 1 1, I'll simply copy it. Multiplying with this one again, I'll place 3 crosses and then I'll just copy it 0 1 0 1 1. So after this, I'll have to add these 4 lines. When I add them up, it becomes 0 plus these crosses means nothing, so it will be 0. 1 plus 0 will be 1, all right. 0 plus 0 plus 0 will be 0, all right. 1 plus 0 plus 1 will be a 0 and a carry 1, because 1 plus 1 will be 1 0. So a 0 here and a carry 1. Now 1 plus 1 plus 1 will be 1 and a carry 1 again, because 1 plus 1 plus 1 will be 1 1. So a 1 here and a carry 1. 1 plus 1 will be a 0 here and a carry 1. 1 plus 1 plus 1 will be 1 1. So a sum here and a carry 1. Now 1 plus 1 will be 1 0. There is no place left to take the carry 2. So I'll place it as 1 0. So this will be the product. Let me see if I've done it right by doing the corresponding decimal multiplication. So let me write the multiplicand. Let me write the multiplicand in decimal. So 1 1 0 1 0 is 26. You can check for yourself. How do I check? See, this is 2 to the power 0, which is 0 into 2 to the power 0 became 0. This is 2 to the power 1, which is 2. Now again this is 0. So this will not be added up. So 2. This is 8, because it is 1 into 2 to the power 3. So 2 plus 8 is 10. 2 plus 8 is 10. And then this is 2 to the power 4, which is 16. So I must add 16 to the already found out 10. 2 plus 8 plus 16. Effectively, I'll have to do. So that is 26. Over here, this is 1 plus 4 plus 8. 2 isn't there. That is 0. So 1 plus 4 plus 8. So that becomes 13. Right? So I've got the decimal equivalent of the multiplicand and the multiplier. If you multiply 13 into 26 using your calculators, or using your pen or paper or whatever way, you can do directly, in fact, also. If you remember the table of 13, right? 13 6 are 78. So 8 comes here. 13 2s are 26 and 7. That becomes 33. 13 6 are 78. 8, and then 7 is the carry, so 13 to the 26, and 7 is 33. So this should come out to be 338. Let us see if this is 338. Let me add them up also like this. 0, this is 2. 2, 4, 8 are not there. This is 16 to the power 4. So 2 plus 16 is 18. Now 32 is not there, 64 is there, right? So 64, and then again this should be 128, 2 to the power 5, which is also not there. But then 2 to the power 8, which is 256. So what I need to do is 256 plus 64 plus 16 plus 2. That will come out to be 338. You can do that and see for yourself. So in addition to counting the binary numbers, we also have to remember the powers of 2. Just as 0 1 1 0 1 1 1 0 0, I'll also suggest that you remember the powers of 2. What are they? 0 1 2 4 8 16 32 64. You know what I'm doing? I'm just giving the powers of 2. 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. So you should also remember 1 2 4 8 16 32 64 128 256 512, then 1024. 1024 is approximately equivalent to 1000. So I'll say 1024 is 1k, approximately 1k. K stands for 1000. We all know kilo is 1000. Now 1024, next is 2048. So I'll call it 2k. Then next to it will be 4096. So that will be 4k. So the counting will be 1 2 4 8 16 32 64 128 256 512 1k 2k 4k 8k 16k 32k 64k 128k 256k 512k, and then 1024k. So 1024k will be 1 mega, 1 m, 1 kk, 1000 k. So that will be 1 m, and then again it will start 2m, 4m, 8m, 16m, 32m, 64m, 128m, 256m, 512m, and then 1024m. So 1024m will become 1 gig. 1000m will become 1 gig. Then it will be 2 gig, 4 gig, 8 gig, 16 gig, 32 gig, 64 gig, 128 gig, you know, 256 gig, 512 gig, and then 1024 gig, and so on. So what you need to remember is the counting in powers of 2. In Hindi we say it 2 4 8 16 32 64 128 256 512 और फिर 1k. फिर इसी तरह k हो जाएगा 2k 4k 8k 16k 32 64 128 256 512 और फिर 1m, फिर 2m 4m 2 4 8 16 32 64 128 256 512, फिर 1 gig, right? So remember 2 4 8 16 32 64 128 256 512, and then 1k. So that you should remember. So we'll stop here, and in the next lecture we will see the complements of numbers, which are very handy. So try to go through this lecture. If you have any questions, email me back so that I can answer those questions, and then in the subsequent lectures. And try to take notes, try to practice a lot. Because the more you practice, the more conversion you will get with the bases other than decimal, and in particular the binary number system that we will be using by all means. Thank you very much.